All right, guys. So in today's video, we're going to be taking a look at how to use computer output in order to find least squares regression lines. The context that we're going to be using for that is going to be Mentos and Diet Coke. I'm hoping that you understand kind of what's going on here. If not, just watch a couple YouTube videos about putting Mentos and Diet Coke. It's a lot of fun, makes a big mess, and so on. Essentially what these two students were looking at is how much Diet Coke is expelled based on the number of Mentos that were put into the bottle. So first thing that it asks us for is what the equation of the least squares regression line is, defining any variables that we use. So if we're looking at all of this information, I can see in my scatter plot that there is a least squares regression line, but notice that in our scatter plot, it doesn't tell us anything about the least squares regression line. And well, I guess I could try to figure it out from the graph. It's not going to be very accurate. The next thing they gave us was residual plot, and that's not going to be helpful at all. I can't do anything with that to get my line of best fit. What I can use is this computer output over here, which gives me a few different things. It tells me a couple of different predictors, one being a constant, the other being the Mentos. It gives me a coefficient, a standard error coefficient, a t, and a p. It also tells me what s, the standard deviation of the residuals, is. It tells me what the coefficient of determination, r squared, is, which is 60.2. And here is the part that we need to focus on for writing our line of best fit. It's going to be these coefficients in this first column. The rest of the information in this is going to be more useful for us in Unit 12 when we start to do inference for linear regression. For right now, we really don't need to do anything with the rest. So constant is going to be our constant value. In other words, it's going to be our y-intercept, whereas our coefficient for Mentos is going to be our slope of our least squares regression line. So if I want to write a least squares regression line using that information, I can define variables if I want to. Y would be most likely soda, X would be the number of Mentos, or I can use them in my equation. I'll choose to go that route and say that soda hat is equal to the 0.07083 multiplied by my number of Mentos plus my constant, which is 1.00208. So now that I've got my least squares regression line, let's do a couple things with it. First, let's interpret the slope of our least squares regression line. What we would say is for each additional Mento placed in the bottle that we would expect 0.07083, and let me make sure I've got the right units here. That was the amount expelled, and the units there was the number of cups. It looks like the amount in cups that was expelled, so 0.07 cups to be expelled from the bottle. The next question asks us about the correlation. Anytime it asks us about correlation, what it really wants us to do is talk about the R value. So if I want to talk about the R value, the first thing I need to do is I need to find it. And while they don't directly give me R, they tell me what R squared is. They tell me that R squared is equal to 60.2%. Make sure to work with that as its decimal form. So if I want to figure out what R is, I need to take the square root of that number. So let's take the square root of 0.602. That's going to tell me that my R value was 0.776 if I go to 3 decimal places. And then we have to be careful about whether we make R a positive or negative, because remember, anytime you take the square root of a variable, we need to look at the absolute value of that number. And in this case, it's going to make sense to keep a positive 0.776 because the slope of our least squares regression line is also positive. There's a positive association there. If the slope was instead negative or a negative correlation was apparent, then I need to make sure that R is the negative value rather than the positive. So interpreting that now, R we would say is more of a moderate strength. So there is a moderate positive association between the Mentos and the Diet Coke that was expelled. In other words, it looks like to some degree, in a moderate sense, as you increase the number of Mentos, the amount of Diet Coke that's expelled is going to also increase. So in D, is a linear model appropriate for this data? Well, we can look at a few different things to determine that. The first would be looking at our residual plot. Do we notice any sort of pattern in our data? And I would say no. It's about as equally spread as you could possibly have it. So is a linear model appropriate? Yes, because the residual plot shows no apparent pattern. We can probably say a linear model is appropriate. Now, if we want to expand on that a little bit more, we could also talk about the fact that our S, our standard deviation of the residuals, is 0.07. So we're only off by about 0.07 cups for on average from our line of best fit, which is pretty good. Now, R squared is somewhat low. We're only accounting for 60.2% of the variation in the amount of Diet Coke expelled. So we could talk about a few other things to say that our linear model is appropriate, but the residual plot is probably enough in this case. Now, are we willing to predict the amount of Diet Coke expelled when 10 Mentos are added? We need to first check to see kind of where our data was collected from. It looks like they collected data from putting 2, 3, 4, or 5 Mentos into a randomly selected bottle. 10 does not fit within that. And so the answer here should be no. This would be an example of extrapolation because 10 is pretty far outside from the rest of our data. In F, on the next page, let's go ahead and do a couple more calculations. We're going to go ahead and calculate and interpret the residual for a bottle of Diet Coke that had 2 Mentos and lost 1.25 cups. So I know that 0.25 or 2 Mentos is going to be my input value X. Let's find what our predicted amount of soda then would be. So we'd say that soda hat is equal to 0.07083 multiplied by 2 plus 1.00208. And then let's go ahead and plug that into our calculator now to see what the predicted amount of soda left in the bottle would be, or rather expelled would be. So we'll take that times 2 plus our 1.00208 is going to be approximately 1.14374. The actual amount of soda lost was 1.25, so we definitely underestimated it since our predicted amount was lower. But let's go ahead and find the residual first, and then we can interpret it. So the residual is, we're going to take our observed 1.25 minus our expected that we just found. So in our calculator, take 1.25 minus that previous value is 0.10626. So what we can say is that we underestimated the amount of soda expelled by 0.10626 cups. And now we are ready to do a couple more interpretations. The first is we're going to interpret our value for R squared. R squared was the 60.2% from that computer output. So we're going to say that about 60.2% of the variation in the predicted number of cups expelled is accounted for by the least squares regression line. Next, let's go ahead and interpret S. Remember, S is the standard deviation of the residuals. From that previous page, we can see that S is 0.0672442. So we can say that on average, the predicted values differed from the actual values by about 0.0672,442, and then cups would be our label here. Last but not least, if the amount expelled were measured in ounces rather than in cups, how would the values of R squared and S be affected? Well, the first thing that let's talk about is R squared. R squared would be unaffected by any change in our distribution. R squared does not have any units, similar to how R does not have any units. So changing the units is not going to change the strength of our linear model. So R squared would not be any different. S would be different. S would be affected by the change in labels. That's because S is something that has a label. In this case, S is your average distance from the regression line, which was 0.067 cups. So when I change that from cups to ounces, that's going to also change my standard deviation of my residuals. So S would definitely be affected. Last but not least, how can you calculate the equation of a least squares regression line using summary statistics, and is this on the formula sheet? The answer is yes, it is on the formula sheet. Here is what you need in order to calculate it. You need to have your summary statistics for each of your two data sets. So you need to have the mean for your X values as well as its standard deviation. You need to have the mean for your Y variables as well as its standard deviation. And you need to have the correlation coefficient between the two, which is R. If you have all of those things, then you can find your line of best fit as follows. The first thing that you would find is your B1, which would be your slope of your least squares regression line. You can find that by taking R multiplied by your standard deviation of Y divided by your standard deviation of X. Once you have your slope, you can find the y-intercept for your least squares regression line, which we call B sub 0 or B null. That can be found by taking your mean for your Y values minus your slope that you just found multiplied by the mean of your X values. And then once you've got both your slope and your y-intercept, then you can write your regression equation as follows, that y hat is equal to your y-intercept b sub 0 plus your slope b sub 1 multiplied by your variable x, and there would be your least squares regression line. So we will see an example of how to do that at the start of tomorrow's class. So we're going to save that next example until then. Until then, have a good rest of your day.